Hello and welcome everyone to our final Earth Week broadcast. My name is Chris. I'm curator for the Daily Planet Theater at the North Carolina Museum of Natural Sciences. And this being the 50th anniversary of Earth Day, we decided at the museum to stretch the celebration out all week long. Today, though, happens to be a very special, extra special kind of day because April 24th is also the 30th anniversary of the Hubble Space Telescope. Today marks 30 years of Hubble Space Telescope in orbit. The Hubble Space Telescope happens to be one of NASA's longest running observatories, and Hubble has captured imaginations worldwide, right? I think with our two presenters today, we're going to see lots of Hubble images, and some of them you may even recognize because they're gorgeous. And this telescope and the research and science that it's inspired have greatly expanded our knowledge of the cosmos. So I want you to meet our very special guests who are going to share their work and their interest in how Hubble plays a role in all of that. First up, I'd like for you to meet the head of the Astronomy and Astrophysics Research Lab at the museum and a professor at the Appalachian State University, Dr. Rachel Smith. Hi, Rachel.
Hi, Chris. Hi, everyone.
And the assistant head of the Astronomy and Astrophysics Research Lab at the museum is Dr. Patrick Treuthardt. Hi, Patrick.
Hey, how's it going?
Doing great. Rachel, how are things in your side of North Carolina in these current times?
Yeah, one day at a time, still going. Happy to do these programs, actually, and think about space for a while. So
you are right. Yeah, we can think about not Earth things for a minute. And Patrick, how are things over in Raleigh?
Oh, it's good. It's nice. You know, looking for my dining room table, so it's a little different, but otherwise it's great.
Yeah, and we've got a good spate of warming up weather.
Mm-hmm.
Yeah.
So it's nice to get outside a little bit too. It's nice to go out and look up at the sky at night, finally.
Yes.
Instead of being cold. So everybody, the way the show is going to work is that if you have questions or comments, you can put those in the comments or in the chat box, depending on whether you're watching on Facebook or watching on YouTube. And as we go, when we get to the end of the presentations, we'll share your questions with our guest speakers. Those chat boxes are open, so please do be respectful of one another and of our guests today. Of course, I know that you will. And the run of the show is going to be that we'll hear from Dr. Rachel Smith first. We'll take a few questions, and then we'll bring Dr. Treuthardt into the show, learn about some of his research and how Hubble impacts that. And then at the end, we'll take questions from both of our guests together. So, Rachel, if you're ready,
I am ready.
Over to you.
All right, let's go. Let's take a look. So hopefully you all can see the first slide. So I am an astronomer and I study forming stars. And so I'm really excited to share some highlights of Hubble's discoveries of star formation, as well as planets, exoplanets, and moons. My research focuses on the chemistry of gas around forming stars. And in fact, I found when I was researching for this presentation, found some really beautiful images that related pretty directly to some of the objects that I study. And as well as looking at our solar system. So we may think of Hubble as looking out into the universe, but actually we've learned a lot about our own solar system from Hubble. So I'll be talking a little bit about that today. And this image on the title slide is really beautiful. It is considered, a lot of the words we hear from Hubble when you look at the images are extreme star formation, extreme stellar death. Stars go through a life cycle and they really go through some extreme events. And here you see this is extreme starbirth in the Carina Nebula. And it's extreme because these stars are blowing out gas and dust. And with Hubble, we're able to see a lot of the features of these regions in the infrared wavelengths, in the visible wavelengths, so what we see every day, and in the ultraviolet So mostly visible ultraviolet, a little bit of the infrared. And when JWST, the James Webb Space Telescope, launches, it will really expand that infrared spectrum. But we'll talk about Hubble today, and happy 30th to Hubble. So a little bit, I have one slide of an overview. Hubble launched in 1990, and there it is shown in orbit. And again, the wavelength. So astronomers, as astronomers, we look beyond the visible spectrum to see features we cannot see with our eyes, with our unaided eyes. And so Hubble expanded what we could see in the visible by magnifying the universe for us, as well as looking at the infrared and the ultraviolet. It was serviced 5 times. Some of you may know that Hubble had a little bit of a mirror problem. That has been corrected for. And the cool thing about Hubble is it could be serviced by astronauts. And so there are astronauts that did these Hubble servicing missions, and they really did these amazing spacewalks. And there's actually an IMAX movie about this. And one of the servicing missions involved putting the camera, an IMAX camera, on the Hubble itself so they could film this, a lot of these repair mission, the repairing of Hubble, and that was really amazing. So if you get a chance to see the Hubble IMAX film, it's really pretty incredible. So I'm going to start with star formation, and one of the most famous pictures of star formation is dubbed the pillars of creation. They kind of look like, they're in the Eagle Nebula, and they kind of look like these, in caves, you might see stalactites coming down from the ceiling of a cave, or just these amazing features that come maybe in the ocean. But actually what's happening in these enormous pillars are stars are forming inside these pockets of dust. So we have millions of stars forming in this one region. And keep in mind, there are stars forming all the time in our galaxy and in other galaxies. And I'm really excited about that because that's what I study. And Hubble opened up this amazing world of star formation. So what you see here is this cool interstellar hydrogen gas and dust. And these are incubators of new stars that are forming there. And so we can learn a lot about just looking at the images and the data from Hubble and looking at these star forming regions. So this is one of the most famous pictures from Hubble. I really like this one too. This is massive stars. There are stars that are different in mass. Our sun is sometimes called one solar mass. It's just our sun. And then we have massive stars that are forming that are many, many times more massive than the sun. And these are the stars that supernova and explode. And we'll look at those in a second. I'll look at some examples. This image is showing massive stars in another galaxy that are shaping their environment. And so they blow out as they're forming, they are taking in gas, they're blowing out gas. And these, what they're doing is they're actually shaping their local environment. And sometimes there's some interesting terminology you might find on the Hubble website. They rock their cradle, I think this one said. So they really are changing their environment on a massive scale. And these scales are many more times more massive than our sun and span great distances in their nebula. This is star formation in Cygnus, the constellation, the Swan, so not very far away. And the star that's forming is right in the center of that image, and you can't actually see it. What you see, the stars that you see here that look like stars are background stars, and they're very, very bright. But the forming star that's blowing out those 2 lobes on the left and right of this image, that star is shrouded in dust. And I was excited to see that this star is actually one that we've been studying, and this is called S106IR. Astronomers have great names for their stars. And this one, we just observed it actually at the NASA Infrared Telescope facility on Mauna Kea, and that's the image you see around me. This is inside the dome of the IRTF telescope in Hawaii. And we were there last year and we're able to observe this star. This is a massive forming star. It's very interesting. The lines you see in that spectrum that I took, those are carbon monoxide. And so the Hubble image is looking at the big region around this star, and the work that we do looking with other instruments is very detailed chemistry of that star itself. So, but we can astronomers often combine data from different observations to create a big picture of what's happening in a region. So this is what it looks like in great detail with a spectrum, and then the Hubble image will expand that view out to see what it's doing in its surrounding area. This is another famous one you may have seen. This is an outburst. Again, kind of when stars have winds and they blow out gas. And this was from January 2002. The Hubble with the infrared wavelengths can see beyond the dust a lot for a lot of images, as long as it's not too deeply embedded in dust. And so we see this view. It opens up this window through the veil of dust around a lot of these regions. And that's what we're seeing here. But again, it's a combination of wavelengths, visible, ultraviolet, and the infrared. This is the Tarantella Nebula. It's in a neighboring galaxy. And again, it's these extreme conditions of star formation and stellar death. There are supernova remnants in this nebula. So a supernova is that big explosion that happens to a massive star. It won't be the fate of our sun because we're too small. We're going to expand out to a red giant and then shrink up into a little white dwarf. But bigger stars can explode, and then really massive stars will explode and then become a black hole. But what's happening here in the Tarantella Nebula, this amazing image of star formation and stellar death. And it's pretty close to us. It's in a nearby galaxy called the Large Magellanic Cloud. So it's an amazing composite of stellar death and stellar birth. This is a really nice image of a young star that's in a haze of gas and dust. And just to remind everyone, all stars form the same way we think. They are collecting material. Our sun the form the same way. So this gas and dust are all around these young stars will eventually form planets. And this is how we form. So we study these regions using instruments like Hubble, the Infrared Telescope Facility, and other telescopes, both on Earth, like on Mauna Kea, or in space. And Hubble is one of those. And so we study these forming stars to also understand our own solar system that form the same way. This gas and dust has got interesting chemistry that will eventually form planets and maybe life. We don't know, but we can't determine that now with the data that we have. But in this image, we see this massive clump of forming stars in the center, and again, all that gas and dust that's forming around it. And so we can learn about the physics of this system and see what's happening using data like and imagery like from Hubble. This is hot, massive stars in the Milky Way. Again, these massive stars really are bright, and we can study them sometimes better than stars that are like our sun because they're more massive and the telescopes can collect more information. And so these are massive stars in this particular nebula that Hubble can see pretty easily, and we can study the regions around it and the cluster as well. Most stars form in clusters, and it's possible our sun had a companion that then got kicked out, and we don't know. But most stars form not alone, but with companions. This is called the cosmic caterpillar. I really like this image and also the way they described it, eating its way through space. These are protostars. And so this is actually, these are very young, kind of like the stars I study as well. And they're still collecting these protostars, these young stars that are not formed yet. They're still collecting material. And what's cool about this image is it looks like a caterpillar. So as it's picking up material, kind of trying to become a star, it's looking like a caterpillar eating its way through space. It's a spectacular image, I think. I really like this one. And these are, you know, again, sculpting their local environment and has this really nice little insect formation that, of course, isn't really an insect, as in case anyone's curious about. This is not life in space. This is just looking like something that's familiar to us, but it is collecting material, and these stars eventually will become massive stars that will probably have planets in the future. This is a really famous image too. It's sometimes used for Halloween when astronomers celebrate Halloween, and they, you know, by presenting really nice images that relate to that because it looks like a witch's broom. And you can kind of see that. This is actually, now we're going from stellar birth to stellar death. And this is a supernova remnant. So when stars explode, they leave remnants of material behind. And these explosions, all this material that came out of a star, these massive stars that explode and create these heavy elements that other systems need to form planets eventually. So as stars die, they seed their regions with materials that are needed for planets to form. And that's how we got here. We use, our solar system was formed from material from exploding stars. And so the, regions like this, Witch's Broom and the Veil Nebula, are really, they're great ingredients for future systems to form. This is another image of a dying star called the Retina Nebula. It's very symmetrical, and as I was reading about this particular image, it was stated that if you could take a spaceship and go around it, it would look like a donut, and with all the material kind of symmetrically around this dying star, and we only see one vantage point. And that's another important thing to remember with astronomy, is we see one point of view from our vantage point. We can't fly to these regions. So we try to get all of this information from a two-dimensional image and create, and understand from models and other types of studies to figure out what's happening around it. Will we eventually have spaceships to go there? Maybe, hopefully, but it won't be for a very long time. So for now, we can study these images and see that we know that this is actually a donut, but we only see one aspect of it. This is a very famous supernova remnant as well, or it's a dying star rather. It's called the Ring Nebula for obvious reasons. It's in the constellation Lyra, and again, these colors are representative of infrared wavelengths, and so they're colored to show different wavelengths in the infrared, so astronomers can study the material around this dying star. This is another one of my favorites called Cosmic Pearls, and it is created, this amazing kind of beautiful jewelry-like ring is created from shock waves from a stellar blast that illuminates material around the blast. And it's quite beautiful. And you can see it's got, there's stars on either side. It really does look like this magnificent piece of jewelry, but it is created from the blast that's coming out of the shock waves from stars. And so it's another one of my favorites. So we're going to go we talked a little bit about star formation and Hubble's discoveries, and now we're going to go to some exoplanetary discoveries. And so as we inch our way to the solar system, rather than the cosmic inch, which is like light years. but this is the first exoplanet, and it's interesting about Fomalhaut B, which, as you can see in that, is actually that little dot in the square that's zoomed out in the lower part of the image. This was thought to be the first image of an exoplanet, the first actual image of an exoplanet, and it was taken in 2004 and then again in 2006. The central star is blocked out because it's very bright, so they have to block it out to see the dust around it. But what's interesting about this is that in 2020, so this year, there was a report that Fomalhaut B has been disappearing. And so why would this exoplanet be disappearing? And astronomers have determined that instead of an exoplanet, it's probably an expanding dust cloud from two objects that smashed into each other. And so this is a really interesting region of planet formation. And so they are making this really cool discovery of objects hitting each other. But so instead of an exoplanet, it's just kind of the remnants of exoplanets, and they crashed in just like you'd have two asteroids hitting each other. So that was pretty interesting. But this is one of the most famous images, you'll see it in textbooks, of exoplanets, and at least studying planet formation using Hubble and other instruments as well. Everything I show you now is from Hubble, but other telescopes have also contributed to the knowledge of these objects. So this is the deep blue exoplanet. This is an artistic rendering. We cannot get such detailed images of exoplanets, but Hubble data led to this rendering of this exoplanet. Instead of being an ocean world, it looks deep and blue like it has an ocean. It actually is a gas giant. So it's a big, huge ball of gas, just like Jupiter would be. And it's about 1,000 degrees Celsius. So it's very, very hot. And some other interesting features is that it rains glass and the rain goes sideways. So probably not a place you want to visit anytime soon. And we can't even get there, but not a great place to think of setting up a colony. Even if we could get there, we'd probably pick a more Earth-like planet. But it is pretty amazing, and they can know this by looking at the spectroscopy and looking at the chemistry around this planet, just like I was showing you we can study with a massive forming star. So this is an interstellar comet. This is just getting more towards getting towards the solar system. This is an interstellar comet called 21 Borisov. It's very active. This is a comet that came in from outside the solar system into our solar system. The image on the left was taken by Dave Jewett at UCLA, and the artistic rendering on the right. And this could have been an ejected planetesimal, an ejected almost planet that came out from another solar system and came into our own. when I was looking at this, I was studying this, and I asked Dave if he had some more information on it, and he sent me these two preprint of his paper that's coming out soon, and these two images were in it, which is really cool, and it just shows you how Hubble can be used. These are Hubble data images, and how they're looking at the tail of the comet, which you can see shooting off in the right, and they can study they can understand the particle size in the tail by looking at the direction that the tail is blowing. And so it's a really interesting paper about understanding the really detailed components of the comet by looking at the direction of the tail. And I was really happy that he was able to send me this. Dave Jewett has spoken at our museum. He discovered the Kuiper Belt, which is, we'll get to that, but he also does a lot of cometary research now. So getting to our solar system now, objects that have been in our solar system since it formed, unlike the Interstellar Comet. We have the inner moons of Neptune, and specifically this image from Hubble helped determine the location of the hippocamp moon, which is shown there in the circle. And so that was very interesting information that Hubble helped determine. We could see in this image there's some of these are faint, but there's actually 6 moons of Saturn in this image. And if you look really closely, you can see there's 2 that are in the lower right of the rings that are pretty faint. But Enceladus is one of them, and I point to Enceladus because it is one of those great locations for astrobiology where we think there's an active ocean under Enceladus, and we discovered water and organic molecules spewing out of Enceladus. So it's a really interesting moon for that reason. But Hubble got this image, and also this great infrared view of Saturn, looking at cloud and hazes in the infrared. So with an infrared picture like this, you can look at different wavelengths and see how the clouds are shaped around Saturn and the haze around it. And so astronomers are able to study that with Hubble. This is Comet Shoemaker-Levy, which hit Jupiter back in the 1990s. And this was the first documented cometary impact on a planet. And it was one of these wake-up calls, right, that comets still hit planets, asteroids still hit planets, which we know because we had an asteroid hit Earth a couple of years ago. And also a reminder that Jupiter has helped kind of take up a lot of the debris that could hit Earth. And so this was a really amazing event to get data for, and Hubble captured this image of where the arrows are showing the little smudges are the comet that was pulled apart from Jupiter's gravity. So this was one of the cometary impact. Comets have hit planets before and could have brought our oceans to Earth as well. The auroras on Jupiter. So we have auroras on Earth. These are energetic particles that interact with our atmosphere, and auroras were also imaged on Jupiter as shown here. So we can study these really great atmospheric phenomena on Jupiter as well. Water was discovered shooting off of on Europa. This was a big discovery. Europa is a little moon on the left. This is a artistic rendering of this, and the bits of blue are the water, where the water was spewing out. Europa is another moon that should have an ocean underneath with water coming out of it. And this discovery by Hubble was a main reason why Europa is a candidate for astrobiology, for sending missions to understand, to see if there's life on Europa, in the ocean maybe. And so this was confirmation that there's water underneath on Europa. 2 new moons around Pluto were discovered in 2005, Pluto being a dwarf planet or a Kuiper Belt object. And those are the 2 moons shown there. And then measuring the mass of Eris, 2 other Kuiper Belt objects are Eris and Dysnomia. And Eris is shown on the right, and measuring the mass of Eris. This was done by Hubble as well. And then my final slide, and I'm excited to take your questions, is that you can help analyze Hubble data. There is a citizen science project called Hubble Asteroid Hunter. Go to zooniverse.org, and you can help analyze Hubble data to identify asteroids in our solar system. So that is all I have, and I'm happy to take your questions. Thank you.
Thank you very much, Rachel.
You are welcome. I should have stopped my share. Did I do that?
Oh yeah, it looks like you did. We're
Okay.
good.
Great.
Yeah, clapping hand emojis in chat for
Thank
Dr.
you.
Smith. Yeah, cool stuff. It's amazing the diversity of research that taking pictures with a telescope can support.
Yeah, absolutely. It is amazing. And both a combination of images and spectroscopy, looking at the chemistry, is what really tells us what's in the universe. And so Hubble has opened up this amazing window that eventually James Webb will take over in the infrared, and we're really understanding a lot about our universe in many aspects, not just galaxies and dark matter, but also on the smaller objects, exoplanets, moons, and such.
So, folks, if you've got questions, you can put those in the chat there on YouTube. We're monitoring that, and we can pose those questions too. One did come in right at the very beginning.
Oh.
Ryan was asking, why is it called Hubble?
Oh, because of Edwin Hubble, an astronomer who was discovered actually, or he came up with the Hubble constant, which gives us the age of the universe. His number was off. He used some stars to try to figure out this Hubble constant, to figure out the expansion of the universe and the age of the universe. Amongst he did a number of other things, but his fundamental discovery was figuring out how do we measure the age of the universe. And his method was not wrong, but the objects he used were not exactly correct. So that has been refined. But yeah, he was a very famous astronomer. He's not alive anymore.
Right. So Glenn's posted a question. What would you say is the most important scientific discovery that has come from Hubble? And maybe in terms of stars, planets, moons.
Yeah, I never answer that question. That's almost like, who's my favorite pet? And there's no favorite. But you know, they're all terrible. No, they're all amazing. But it's you know, I can't answer that. I would say, you know, it's almost like, what's the most important thing we don't know about, or what will we discover? I think in fact, what Hubble has opened up in our own solar system is fascinating, looking, you know, to confirming that there's water on Europa. And to me, that's amazing, because if, you know, we need to go to Europa, that helped leverage this mission to be approved to go to Europa Clipper. And so I think that's one of the most amazing discoveries, is seeing, you know, catching that plume of water like a geyser shooting off of Europa, because water is where what we think life should be. And so I wouldn't say that's necessarily the most amazing, but it is one of the amazing ones. And you know, finding the Interstellar Comet information. I mean, to find an object that is from another system that's in our own solar system is fascinating. And so these are some highlights. Yeah, it's a hard question to answer. There's so many discoveries.
Yeah, I was wondering if maybe a better question would be, what are some of the more surprising discoveries, things that Hubble saw that we didn't expect to see?
Oh, that's a good way to phrase it. Well, I'd say as a scientist, you know, it's an interesting question, because we don't really expect to find things. We perform experiments, we perform studies, and we hope to get good data, and we don't always know what we're going to find. And so whether something's surprising or not, I think all of the discoveries we see from Hubble and from other research, other telescopes, other missions are important, because they were not predicted, and so necessarily, and so, you know, as a scientist, we don't say we're going to find this and we'll see if we find it. It's mostly, you know, designing a good experiment to collect good data. And we know, for example, that there should be gas around a star, but what that gas is going to tell us, we don't know. So, yeah, I mean, it's a good question. I can't really answer that so well about what was of all the. I mean, there were 1.5 million or more images taken from Hubble. So which of those were most surprising? I can't really answer that, and it might depend on whose study you're talking about or who's making that claim. So, yeah.
So one more for you, and then
Sure.
we're going to switch over to Patrick. But when astronomers are using Hubble data, is it that they get these images, almost like you would just pin a picture up on the wall and then study the picture? Or do you convert these images into other kinds of data? You know, are there numbers that come from the telescope? Or is it just really these images and we go from
Yeah, that's a good question. It's not the image that has to be processed. And so how the data come in, you know, I've not gotten data from Hubble. I can tell you that it's definitely not an image that lands on your desk. they are either cubes or tables of data that you then process. And so they are basically numbers, right? And so then these are processed into images that, so like I said, I don't know how the data are formatted. They're probably in some kind of file. Like I get data in a file called a FITS file, and it's basically a list of numbers that then we convert, I convert that into a spectrum, which I showed you with all the little lines. And you can also get images from the data there. So they are coded, and then the astronomers will take that and process that into whatever kind of data it is, whether it's an image file or a spectral file. And then you see that converted file into the colors that we see. Of course, it's false color in the sense that they're not, if we flew out there, they wouldn't be in all these rainbows, but they represent either chemistry or wavelengths in the infrared or something like that. And so they are spectacularly beautiful, but they're not optical, all of them. So a lot of these clouds that we see in these beautiful colors would be kind of invisible if we were out there just looking with our eyes. So they're processed is the answer.
Great, thank you.
Thank you, Chris.
And so everybody, Rachel will be back at the end of the next presentation too. So if you come up with more questions, stars, planets, exoplanets, moons, stick around. We'll have a longer Q&A session at the end as well. But let's go ahead and meet Dr. Patrick Treuthardt, Assistant Head of the Astronomy and Astrophysics Research Lab. Patrick, are you with us? Somewhere in
I am.
out there on the internet.
The host has stopped my video. There we go. Cool. All right. Well, thanks. Yeah, thanks for having me. Let me share my presentation. All right. Yeah. So Rachel talked about basically things within our own galaxy that Hubble has seen, the Hubble Space Telescope has seen, and I'm going to talk about things that Hubble Space Telescope has seen outside of our own galaxy. So we're going to move our way outward. And so this image that I'm showing here on the background of my slide is it's called Stephan's Quintet, and what this is just a bunch of galaxies that are physically close to each other, except for that bright blue galaxy in the bottom right corner. That's actually a foreground galaxy, but it's just an example of some of the things that the Hubble Space Telescope has seen outside of our own galaxy. And so what I'd like to do is actually talk about Edwin Hubble, who the Hubble Space Telescope is named after, and so like some of his major work and how the Hubble Space Telescope has actually advanced that. So Edwin Hubble, initially he wasn't an astronomer. He started out he started moving in the direction of law, because his dad actually wanted him to become a lawyer. And then his dad actually died in 1913. And after that, he went back to school and pursued astronomy. And so he was all around a smart guy to begin with, but he was really devoted to his family and to his father. And after his father died, he felt like, okay, now I have the freedom to actually, pursue his interests. So he ended up getting a PhD in astronomy, and it was in 1917. Which was the end of World War I, but he immediately enlisted to actually fight in World War I, but he never saw any action. And then World War I ended, then he became, he actually really started his career as an astronomer. And he did a lot of his major work in the 1920s. So in the early to late 1920s is when a lot of this stuff he came up with really blossomed. So one of these things that he came up with was he basically expanded, he basically showed us how big the universe is. So initially when we looked out at the night sky, we would see these things called like spiral nebulae, and nebulae were just, they were just thought to be these gassy objects, in the sky. And we didn't know if they were part of our own galaxy or if they're galaxies in their own right. So it was really unknown. And so what he ended up doing was he ended up using a relationship discovered by an astronomer in 1912 named Henrietta Leavitt. And what she found was that there are these types of stars called Cepheid Variables. And these are stars, these are variable stars that vary in a very predictable way. And what that means is basically they tend to pulsate, and their pulsation rate corresponds to how intrinsically bright they are, just what's called their luminosity. So if they pulsate very quickly, then they tend to be dimmer intrinsically, or if they pulsate, if their period of pulsation is longer, then they tend to be brighter. And so with these, if we look at these Cepheid variables, we can actually use these as something called a standard candle. So imagine, you just have, a box full of candles. They're all the same. If you light one, you put it really close to you, you know that it's very bright. But now if you take another one of these candles and you move it much further away, by measuring how bright it is, you can actually determine how far away that candle is from you. And so by looking at these Cepheid variables, if we know the relationship between how quickly they're pulsating and how that relates to how bright they really are intrinsically, now if we put these at different distances, we can actually measure the distance to these Cepheid variables. So we know how far away they should actually be. And so when we look at the Milky Way, we can look at Cepheid variables within the Milky Way, and we can actually determine the size of the Milky Way based on where these Cepheid variables are. And so now we know that the Milky Way is actually between 100,000 and 200,000 light years across in diameter. Depending on what you're actually measuring, what you're actually really thinking about. If you're just talking about like the extent of the stars, it's about 130,000 light years. If you're talking about like, all the dark matter that it contains and things like that, it's closer to 200,000 light years. So it really kind of falls in between there. But so when we throw out these numbers, it's hard to imagine what 200,000 light years is. So this guy, James O'Donoghue, who creates these fantastic visualizations, he actually created what I think is probably one of the best visualizations I've ever seen to kind of give you a sense of how big the universe really is. So the speed of light is the fastest anything can go in the universe. And so this is an animation showing you in real time the speed of light, and as a beam of light travels between the Earth and the Moon. So from the surface of the Earth to the surface of the Moon, it takes about 1.25 seconds to travel that distance at the speed of light. So basically, if you send a signal from the Earth, like a radio signal or a beam of light, you send it to the Moon, and then it comes back from the Moon. It actually takes 2.5 seconds before you get that signal back. Once you send it, it takes 2.5 seconds until you get it back. If it just bounces and comes right back. So, and the Moon is the closest celestial object to us, and it still takes 2.5 seconds for light to get there and come back. Now, Mars is one of the planets that's closest to us, and Mars's closest approach puts it at 55 million kilometers away from us. So, it actually takes light or a radio signal 3 minutes to reach the surface of Mars from the surface of the Earth. Now, we're not going to watch this whole video, but you get a sense of just the vast distance between the Earth and Mars, and when Mars is at its closest approach. So really, if this signal were to turn around, it would actually take 6 minutes from when we send a signal, it bounces off Mars and it comes back. So, and this is one of the closest planets to us. So now if you imagine 100,000 light years to 200,000 light years, I mean, the distances are just enormous. It's ridiculous. So one of the things that Edwin Hubble did was he looked at these spiral nebulae, and one of them was this thing called the Andromeda Nebula at the time. Now we know it as the Andromeda Galaxy. And this is one of the few objects that you can see with the naked eye that we now know is not part of our own galaxy. This is actually a galaxy in its own right. And here you could see it in a very dark sky near a telescope. But you can see it's a fuzzy object. But if you actually look at it with a telescope, you can actually see that it has some spiral structure to it. So what Edwin Hubble did was he used one of the largest telescopes in his day and looked at the outer edges of at the time, Andromeda Nebula, and he looked for Cepheid variables, and he managed to find some. And from that, he was able to use them as standard candles to figure out how far away the Andromeda Nebula was. And he determined that it was about 2.5, well, now we know it's about 2.5 million light years away, which is far beyond the extent of our own galaxy. So this actually has to be a galaxy in its own right. And so by Edwin Hubble finding these Cepheid variables in this nebula, we now know that these spiral nebulae are actually galaxies in their own right. So this actually pushed the boundaries of the universe. At first we thought that our universe was the Milky Way galaxy and everything was contained within it. But now we know that the Milky Way galaxy is just one of many galaxies in the universe that we can see. So this actually, Edwin Hubble actually pushed the boundaries of the observable universe. Now, the Hubble Space Telescope actually went far beyond that, obviously. So one of the things that the Hubble Space Telescope did was the scientists ended up doing was they wanted to just kind of do an exploration of the night sky. And what they did was they picked an apparently blank section of sky, away from any stars in our own galaxy, and they just stared at it for a long period of time, for I think it was a total of 50 hours. And this became known as the Hubble Extreme Deep Field. So to give you a sense of how big that field of view is, this box here that I show you on the right with the moon in it, this box is 1 degree by 1 degree in your field of view. And the moon is about ½ degree in your field of view. So this little box, the XDF box, this is the Hubble Extreme Deep Field. This is 1/25 of a degree. Now, to give you a sense of how tiny that little space is, so obviously a circle contains 360 degrees. So 1 degree is 1/360th of that. So again, just by looking at this, you can see that 1 degree is actually very, very tiny compared to your overall field of view. So if you really want to get a sense of this, this is something that you can do like right now if you want to. If you actually sit back, you extend your arm, and you extend your pinky and you close one eye, and you look at something at the far end of your room, your pinky takes up about 1 degree in your field of view. So you can cover up things, in your room or in your house, and you can see what takes up, less than 1 degree in your field of view. So again, the moon takes up about ½ a degree. So if you go out at night or during the day, if you can see the moon, actually it's cloudy for me right now, but if you go outside, you see the moon, you can actually cover it up with your pinky if you do this, because it takes up ½ a degree. So 1/25 of a degree is very, very tiny. So it's a very tiny section of sky that the Hubble stared at for about 50 hours. And so when it did that, this is what it saw. It ended up seeing just an enormous amount of galaxies in what was thought to be an apparently blank section of sky. They didn't know before this, they had no idea what was in there. They just thought, okay, we're just going to explore and just stare at this section of sky to see what was there. So when you look at this image, every little bit of light, every little speck of light, every little smear that you see is a galaxy in its own right. And they estimate there are about 10,000 galaxies in this image alone. And some of these we've now been able to measure. We think that some of these are, the furthest ones are about 12 billion light years away. So this is, basically right near the beginning. These are galaxies very close to the beginning of the universe. So it's just ridiculous. So the only things in this image that probably aren't galaxies are these things that I'm pointing to with arrows here. Although there are 2 sets of 2 arrows, and I think the left 2 arrows are they may actually be pointing to galaxies themselves, just really bright galaxies. But the arrows to the right, those are actually stars within our own galaxy. Those are bright stars that happen to be in the field of view. But everything else that you see in this image is a galaxy. And so if we extrapolate this out, if we look at this 1/25 of a degree section of sky, and we extrapolate this out to the entire sky, we now think there are about 2 trillion galaxies in the observable universe, which is just an enormous number. Each one, let's say having 200 billion stars in them. Just ridiculous. These numbers are enormous. It's just crazy. So another thing that Hubble did, which is slightly less important, but still very interesting to me because I study galaxies, was that he developed a classification system for galaxies. So he saw that all these spiral nebulae and all these different types of nebulae, which we now know are galaxies, and he actually put them into bins. So just like when you go out into like a forest for the first time, you start seeing all these different trees and shrubs and things like that, and you start putting them into bins, right? Like you come across this large variation of different things, and you want to start organizing them. So you say, okay, these are trees, these are shrubs, these are different types of trees, these are like coniferous trees or deciduous trees, things like that. And so Edwin Hubble did the same thing. So he came up with a classification system for galaxies. And he saw that there were basically 2 main types of galaxies. There were elliptical galaxies and spiral galaxies. So, and he came up with this tuning fork diagram to kind of organize it. So ellipticals are on the left side, spirals are on the right. And if you imagine taking an elliptical galaxy, it's basically just a giant ball of stars with no real structure to it. So they range from very circular to very elongated, and they're basically like hoagie buns. So if you imagine taking a hoagie bun, right, and you rotate it around, it basically looks the same, and no matter how you rotate it, there's no real structure. There's nothing really, super exciting about it. Spiral galaxies, on the other hand, they tend to have a lot of structure. So if you look at these images surrounding the cartoon drawings, you can see these spiral galaxies actually do have a lot of structure to them. And so they basically look like pinwheels, right? They have arms, they have a bulge in the center. And if you imagine, they're actually very thin objects. So if you imagine taking two DVDs and stacking them on top of each other, that's basically the ratio of thickness to diameter for spiral galaxies. They're very, very, very thin objects. And so he noticed when he looked at spiral galaxies that you can actually divide them into two major types of classes. There's something called barred spiral galaxies that you see on the bottom part of that tuning fork, and something called what we call now non-barred spiral galaxies near the top. And these barred spiral galaxies, they tend to have a bulge in the center and then a linear structure coming, passing through the bulge, and then you see the arms coming off the ends of that linear structure that we call a bar. And so there are barred spiral galaxies and normal spiral or unbarred spiral galaxies. So what has a Hubble Space Telescope shown us about galaxies? So for instance, if we look at this one right here, this is NGC 1300. And if we look at this galaxy, this is a Hubble image of that galaxy. And you can see there's a tremendous amount of detail going that you can see in this barred spiral galaxy. And one of there's people have been studying this galaxy forever now. And so there's just a lot of, it just produces so much information. So all the blue light that you see there, all the blue stars are showing you really young stars, newly formed stars. You can see the dark bands cutting through there. That's all dust obscuring starlight. You can see in the center, all the starlight actually looks more yellowish orange. Those are actually older stars. So you can see the bars actually really composed of much more older stars, but there's two lanes of dust on the leading edges of the bar. If you imagine the bar rotating in the direction of the winding, it just you just get a wealth of information about the structure of this galaxy. Other things that Hubble has imaged, galaxy-wise, one interesting thing is this object called NGC 3314. And basically what you're seeing here is two spiral galaxies with one overlapped on top of the other. So they're not actually interacting. They just happen to be in a chance alignment in our line of sight. So one is much further away, the background one is much further away. And then we have a face-on spiral galaxy in between the far-away galaxy. And what's happening is the far-away galaxy is actually backlighting the nearby galaxy, the face-on nearby galaxy. And you can actually see the dust structure go all the way into the central nucleus of that galaxy. So it's actually backlighting and showing you the dust structure all the way down to the center of the galaxy. It's just a remarkable chance alignment. It's really very interesting. We've actually taken closer looks at really rare objects. So this is called Hoag's object, and it's unclear how something like this forms. And so we've seen objects like this called Hoag type objects. This is the prototype object, and it's really not clear how something like this forms. How you get a very bright, central circular object in the center that's composed of old stars, looks like an elliptical galaxy with a bright blue ring of star formation surrounding it. And it's really strange that something like this happens. And we think that they are maybe 0.1% of all observed galaxies in the universe. So they're actually very rare objects. So the weird thing about this is if you look in the top, between the ring and the central object near the top of the galaxy, you can actually see what looks like another Hoag type object way in the background. That's weird. I don't know if that really is or not, but it's actually very strange that happens to be in the field of view. Another thing that Hubble has done is the Hubble Space Telescope has done is shown us, basically it's helped confirm like general relativity. So if we look at clusters of galaxies, so what you're looking at here is a cluster of galaxies, and you see those arcs that kind of make what looks like a smiley face. This is actually light being bent around that group of galaxies in the center. So that's actually a galaxy in the background, and its light is being bent around it. So this actually confirmed Einstein's theory of general relativity. And it also shows us the mass distribution of those central objects as the light's being bent around it. So it actually tells us something about the dark matter contained in this, and basically where all the mass is distributed in that object. So the Hubble Space Telescope has shown us that as well. And even if we look at some of these, what I call little less interesting galaxies, these elliptical galaxies, we actually learn a lot about those as well. So this is a giant elliptical galaxy called M87, and obviously, it doesn't look very interesting. I mean, it just looks like just starlight just kind of smeared out. It's very bright in the center, and then it just kind of fades out. But if you look closely, there seems to be a line coming out of the center there. And so if we zoom in on that, again, these are Hubble images here. And if you zoom in on that, so on the left side, it's actually been colorized. That line has been colorized. And on the right side, that's actually a further zoomed in image of that line. And what that is, that's actually a jet of material being ejected from the nucleus of that elliptical galaxy. And so if we further zoom in on that, and now we get into artist renditions, because even the Hubble can't show us way down into the nucleus of this galaxy. So this is an artist interpretation of what we're seeing. So if we zoom way in, what we think is happening is, if we zoom in toward where that jet is coming from, we think there's what's called a dusty torus. So it's basically a donut of dust surrounding a central object that's producing those jets. So if we zoom in to, So if we zoom in to inside that donut, what we think is in the center is actually a supermassive black hole with material falling into that black hole. And as that material falls into the black hole, it heats up, becomes very energetic, produces magnetic fields, and then sends charged particles shooting perpendicular to the disk of material out into space. And so what we're seeing is actually that jet from the very nucleus of that galaxy being shot out way out into space, and that's what we're actually able to see with the Hubble Space Telescope. And so this is an animation on the right side created by the Event Horizon Telescope team, showing you what we think is happening very close to that supermassive black hole in the center. And again, this is not done by the Hubble team, but this was produced within the last year. And what the team has done is they've actually been able to image that disk around that supermassive black hole. And on the right-hand side is the actual image of that disk around that supermassive black hole. So that was actually very, very interesting. But so what the Hubble Space Telescope has done is not only shown us some evidence like that of actual supermassive black holes in the centers of galaxies, but now the Hubble Space Telescope has actually taken like what's called spectroscopy of the nuclei of many galaxies, and has found evidence that essentially every single galaxy that we look at seems to have a supermassive black hole in the center. Just basically every single galaxy. And so it's unclear where these things come from, but they're very, very large. So one of the largest supermassive black holes, if you imagine, so these supermassive black holes range from millions to billions of times the mass of the sun. And one of the biggest ones is maybe 17 billion solar masses, 17 billion times the mass of the sun. And if you imagine this black hole completely dwarfs the Earth's the solar system itself. So that ring, the blue ring that you see in the center of this image, is actually Neptune's orbit around the sun. And this black hole of a 17 billion solar mass black hole is actually 4 light days across. It's enormous. And so we even see evidence in our own galaxy, in the Milky Way, of a supermassive black hole as well. And we've been able to measure it to be about 4 million times the mass of the sun. And it's contained in a diameter that's only 17 times the diameter of the sun. So the only thing that it could be is a supermassive black hole. And what you're seeing here, these are, on the right side is time-lapsed images of stars orbiting that supermassive black hole. And the left side is basically like just a cartoon kind of animation showing you the same thing. So finally, the other thing that Hubble did that Rachel actually alluded to in one of her answers was that he also discovered a relationship between how far away a galaxy is and how fast it seems to be moving away from us. So he discovered something called basically he found a relationship between the distance to a galaxy and the recessional velocity of a galaxy. And so in one of his papers, this is a plot from one of his papers, and what he showed was that as you looked at galaxies that were further and further away from us, it looked like they were moving faster and faster away from us. And so that was actually a really interesting result, in that, based on how fast a galaxy is moving away from us, you can now kind of predict how far away it is. Or if you're able to measure its distance, you can kind of predict how fast it should be moving away from us. And so what does that mean? Why is every galaxy that we look at, why does it generally seem to be moving away from us? And the answer to that is most likely that the whole universe is expanding and all of these galaxies are along for the ride. So if you imagine the universe being, a giant loaf of raisin bread, and you put it in the oven, and as you bake it, those raisins are all going to separate away from each other as the loaf increases. And so, and basically, every galaxy a galaxy is one of these raisins in this raisin bread, and as the universe expands, it's basically carrying all these galaxies away from it. So what Hubble did with this result was they actually provided evidence that the universe is actually expanding. And so again, he also expanded our minds as to what the nature of the universe is and what it's actually doing. So he actually, again, pushed the boundaries of our understanding of the overall universe. And so from Edwin Hubble, based on his results, he was able to kind of estimate the age of the universe from this data. So basically, the idea is that if the universe is getting bigger as time goes on, at some time in the past, it must have been smaller. So if you're able to measure, the distance to, let's say, the furthest away galaxy, how long did it take to get to that distance? So if it's 2 billion light years away, maybe it took 2 billion years to get to that point, as an example. And so Edwin Hubble, for instance, managed to estimate the age of the universe to be about 2 billion years. But again, this was in the 1920s, 1930s. But then, as time goes on, in the meantime, we were able to kind of constrain that more and create better estimates. But before the Hubble telescope, we were only able to estimate the age of the universe to be between 10 and 20 billion years, which is still, there's a lot of room in that. But after the Hubble Space Telescope, with all the data it was able to collect, we've been able to refine that down to, 1/10 of a billion years. So basically 13.7 billion years. So we're able to get that down to a pretty narrow estimate. So this is how old we think the universe actually is now. And so finally, so what can the Hubble Space Telescope actually tell us about the fate of the universe? Well, if the universe is expanding, what's actually going to happen to it, as time goes on? Well, where we currently are, it's kind of hard to say. Could it be that it's expanding and then at some point, all the mass in the universe is going to kind of grab a hold of it, the gravitational force is going to grab a hold of it, and it's going to collapse back in on itself? Will it just keep expanding and kind of just decelerate but never really stop expanding? Or will it just keep coasting and just keep expanding at at a constant rate? Or could it expand and then expand faster and faster as time goes on? And so what the Hubble Space Telescope, what scientists have done with the Hubble Space Telescope is they've looked at a type of supernova called a Type 1a supernova. And what these things are, again, like standard candles. So they're like Cepheid variables, in that every time one of these Type 1a supernovas explode, they're basically the same. They're always the same brightness. And the reason is because what it is, it's two stars in orbit. One is a very massive, like red giant star, and the other one is a white dwarf star. And the red giant will dump mass onto the white dwarf star until until enough mass is reached on that white dwarf star that basically it ignites and then explodes in a supernova explosion. And so this process is pretty much always the same. And this is why a Type 1a supernova, when it explodes, it's always the same brightness. And so we can use this as a standard candle. And because they're incredibly bright, we can look for these in very far away objects. We can look at these in distant galaxies, that are like 12 billion light years away, for instance. And what has happened is, by using these standard candles, we're able to accurately measure distances to these galaxies. And based on that relationship, that velocity-distance relationship that Hubble created, we found out that it actually, that line actually bends. And what that means is that as time goes on, as time goes on, we're not actually slowing down, we're not coasting. What we found out is that the universe is expanding, but it's actually accelerating as time goes on. The expansion is actually accelerating. So that means that the universe is getting bigger and bigger, faster and faster as time goes on. And this actually led to the first evidence for something called dark energy. So the only way you can accelerate something is by basically adding energy to the system. So just like, you can coast in your car by taking your foot off the gas, by, not adding energy to the system, and you can just coast in your car. But if you want to accelerate, you got to push down on the gas pedal and add more fuel to the system, add more energy to the system so you can go faster. And so that's why this is like the first kind of real evidence for dark energy, that this is where the idea for dark energy came from. And the reason why we call it dark is because we don't know what it is. All we know is that it has to be some type of energy being input into the system to help with this acceleration. So anyway, so that's basically my presentation about what Hubble has done, both Edwin Hubble and the Hubble Space Telescope. So if you have questions, I'd be happy to answer any questions you have.
Thank you very much, Patrick. Clapping hands emojis in the chat for Patrick too. And Rachel, I think if you want to jump back on too, that would be great. We'll just go ahead and bring everybody.
Here I am. Hi.
Welcome back.
Thank you.
So, Patrick, tell me a little bit about your research studying galaxies and how you use or don't use information from Hubble.
Well, so I don't actually use a lot of information from Hubble. So I have worked on a project where okay, so some Hubble data I have used some before is, so when we look at those galaxies, so for instance, if we go back to that, if you remember that galaxy NGC 1300, that barred spiral galaxy where you can see the dust lanes in it, there's a relationship between how strong that bar is, how much gravity that bar actually has, and the curvature of those dust lanes. So I'm actually, I study galaxy morphology, which means I study the shapes of galaxies and the structures in galaxies and what that can tell us about things that are harder to measure. And so one project I had was actually trying to measure the curvature of those dust lanes in barred spiral galaxies, so that way we can determine how strong those bars actually are. And so I've actually used some Hubble data for that. But like a lot of the projects that I work on is basically looking at shapes of galaxies and kind of determining, what can that tell us about supermassive black holes or dark matter in galaxies, things like that.
I'm looking at the YouTube comments, YouTube chats. Eric really likes the loaf of raisin bread analogy. Where did you get the raisin bread from? Is that yours?
No, that was a GIF I think I found on Giphy or something like that. Yeah.
Oh, okay.
Yeah.
Eric was wondering who coined that analogy.
Oh, so that's actually, yeah, that raisin bread. I think that's just a basic analogy that everybody uses, like in introductory astronomy. So I mean, it's a good one actually. So I kind of like that. The other one people tend to use is if you imagine taking a balloon and drawing dots on it, and as you inflate the balloon, the dots all move away from each other. But that tends to confuse people and students because they're like, well, what's on the inside of the balloon? You have to say, well, all of space is the balloon. It's not, inside doesn't count. So the raisin bread actually works a little bit better because it's actually 3-dimensional rather than 2-dimensional. I
like it. It. And I guess I like raisin bread. Okay.
Yeah, it's all right.
Rachel, I'm curious, the way we think about the expansion of the universe and using standard candles to measure the distances between the galaxies, can you do something similar with stars and exoplanets? And do we see things closer to home, like within our own galaxy, moving away from us in a similar fashion? Is everything expanding?
No, and so the galaxy itself isn't expanding. As far as I understand, right, Patrick and Craig, is just the universe is expanding and everything's moving farther apart. And stars, really, the star forming regions we know from looking at the spectra how far away they are, and that really isn't changing. And so we have ways to measure that looking at the spectroscopy of the lines, and that pretty much stays the same, in the time that we're observing them. So we don't see this great expansion close to home in the star forming regions. But eventually, billions, trillions of years from now, the idea is that we won't have, everything eventually there'll be no more star formation, and the universe will have expanded and everything will be pulled so far apart that there won't be anything left, and there won't be any more energy the universe. This comes into like there's science fiction stories written about this, and so that is so far in the future, trillions of years from now, that I guess we don't really worry too much about it. I don't know if Patrick has something to add to that, but yeah, so we don't see the same scale in particular star forming regions.
Yeah. So yeah, right now, because you can only really measure that expansion at very large distances. So between like clusters of galaxies or galaxies. So it's hard to see that, you know, on small scales, especially within our own galaxy, because the gravitational pull between like all the objects within our own galaxy basically counteract that expansion. But as the expansion accelerates, and you know, again, like Rachel said, trillions of years from now, you know, way into the future, as the expansion rate is really fast because of that acceleration, eventually things are going to be so separated, and the fabric of space is going to be stretching so fast that it will actually start to pull things apart. And that's the ultimate fate of the universe, is something called the heat death, where everything just kind of cools out and stars won't form anymore. You know, you won't have galaxies, things like that. And it just becomes a very cold, dark, dead universe.
There's a short story, The Last Question by Isaac Asimov, that goes through this. You can get it online. So if you want to read a really good short story about this, The Last Question, it's pretty famous.
Okay.
At the very end of time.
All right, let me throw some more questions at you. Look, Patrick, you mentioned the speed of light. Nothing can go faster than the speed of light in the universe. Laura is asking, how fast is the speed of light?
It's 300,000 kilometers per second. So I don't know. I mean, it's fast, right? So I don't know. I don't know. I mean, it's like, again, it's, you know, these numbers are huge. It's hard to really put that into perspective. I mean, it's, you know, again, like I think those animations made by James O'Donoghue are just the best way to actually kind of put that into some kind of mind frame, right? Because it's just there's no way to grasp these numbers anymore when they get that big.
Yeah, I mean, yeah, I've seen presentations you've given similar to this one, and seen you use that animation before, and it really does send a pretty clear message, you know, about how fast light really is. That if we bring it down to a scale that we can recognize, kind of like the raisin bread thing, right? These really help us understand more about the scale of the universe.
Yeah.
Is there any evidence for very eccentric shapes of galaxies? Eric is saying like a torus. Or is like a Higgs object kind of like the eccentric thing?
I mean, like specifically a torus, I can't think of one that looks like that. But you can get really weird shapes, and those are like the really weird shapes you generally get are from when you have galaxies interacting with each other. So if you have two galaxies colliding with each other, or passing through each other, or passing nearby, you can get weird shapes out of it. But just a galaxy on its own, yeah, I mean, they tend to be very, you know, if you leave a galaxy alone long enough and it's spinning, it'll just kind of reach like kind of an equilibrium state where it looks pretty symmetric, and you get some you know, you get some interesting features out of it, but it'll be very regular. But like really weird stuff happens when you get galaxies colliding with each other, you know, depending on what time you're looking at it. But yeah, like a torus specifically, I can't think of an example where I've seen something like that. It's not to say it doesn't exist, but I can't actually think of one that looks specifically like that.
And if we're talking about the shapes of things, when we bring it down to a smaller scale, like these gas clouds, they just come in all kinds of random shapes.
Right? Oh, the blobs of the clouds of gas. Yeah, they look like clouds in the sky. I mean, they're gas and dust, and they don't have that kind of refined shape unless you're looking at a huge like supernova remnant, or we sometimes see, like I was showing, the little pearls. And sometimes you can make out shapes that we think of as conventional shapes. But most of the time, the nebula, that we see, the star forming regions, they are described like the pillars of creation or the caterpillar, but really they're just big blobs of somehow gravitationally bound gas and dust. And they you know, they kind of do look similar to clouds in the sky, although on a much more massive scale.
Here's another question. Do elliptical galaxies rotate like spiral galaxies do?
No. So yeah, that's one of the differences between ellipticals and spirals. So so basically, elliptical galaxies have, the stars in elliptical galaxies have a lot of random motion. So there's, if you imagine like the central part of a galaxy, right? Then you have stars kind of in very elongated orbits and passing in random directions through the center of that galaxy. So it's very, very like, randomly, those orbits are very, very random. And so they're, kind of scattered all over the place. With spiral galaxies, if you look, because they're very flat and disk-like, they tend to be mostly in rotational orbits, and there's very, very little scatter in random directions, except when you get to the bulge of a spiral galaxy, when you get to the very, central region of a spiral galaxy where you have, that roundish kind of bulge there, that's actually random orbits from stars there. So really, the bulges of spiral galaxies are similar to elliptical galaxies in general, but then the disk part of a spiral galaxy is rotationally supported as opposed to random orbits.
All right. Well, Rachel, Patrick, thank you very much for doing this. Thanks for being
Great.
here.
That was
Thanks a
really
lot.
fun. Thank you
Thanks.
for all the programs, Chris. It was fun doing this together.
Yeah, we've had a great Earth week, haven't we?
Yeah, I think we've had a great Earth week, a space week too. So
Yeah, right.
it's been great.
We've covered just about all topics
All the topics.
I mean, we did sharks, we did conservation, now we've done galaxies and stars and planets. So we've been all over the place.
Yeah.
But had
But
a
we
lot
are
of
a
fun.
planet in space, so space, we got to think of space too. So yeah, I think it all connects really well.
We just bring it all right back down to home.
That's right.
Home being the universe
That's right.
that we live in. So, Patrick, Rachel, thank you so much. Happy
Thank you.
Earth Week. And we'll probably be connecting and chatting more about space very, very soon.
Awesome.
And hopefully very soon in downtown Raleigh at the Museum of Natural Sciences.
Hopefully.
Awesome.
Everyone stay safe.
Yeah.
To everybody watching, thanks for tuning in and joining us for today's program. Keep an eye out on naturalsciences.org for upcoming programs, and follow the museum on Facebook, Twitter, and Instagram at Natural Sciences is where you can find us. There you can get updates on all of the great programs and offerings that we still have coming at you from the North Carolina Museum of Natural Sciences. And we're going to keep doing more live streams, so you will definitely want to subscribe to the museum's YouTube channel. Click the bell to get notified. That way you know when we're going live here on YouTube and when we're uploading new videos. Thanks everybody for tuning in, and have a great Friday. Take care, everybody. Bye.